Okay, I really wanted to keep these down about 5 or 6 minutes per problem, but I guess we kind of did. But I kind of go off on tangents sometimes, I guess. But I think they're good. I know it sounds like I'm rambling sometimes, and I can't. Sometimes I have a hard time listening to myself. But anyway, so here we go. A satellite M is equal to 500 kilograms, orbits the Earth at a distance of 198 above the surface of the planet. The radius of the Earth is this, and the gravitational constant is this, and the Earth's mass is this. What is the speed of the satellite in meters per second squared? So we're assuming a couple things. One, we're assuming a perfectly circular orbit, which is not true exactly. It's a little mooshed. You know, there's an apogee and a perigee. And there's in orbits, but it's round enough for our purposes. And so remember this is a fun one because we know that the centripetal force, the net force, is equal to mv squared over r. So this is a piece of cake. We know that the net force is equal to mv squared over r, and I think this might be a homework problem, but I'm not sure. So let's go through it, and let's write down the data that we know. First of all, I'm going to change that 198 kilometers to 198,000 meters, and make that 1.98 times 10 to the 5th meters. Okay, I got to put everything into terms of meters. So let me write down the data that we know. The mass of the satellite is 500 kilograms. We need to figure out, and I think I'll bet $1 to a donut the mass is canceled, and I could care less about its mass. Its orbit is 1.98 times 10 to the 5th meters. Okay, and it's above the. That's its distance above the, and the radius of the Earth, RE, is equal to 6.38 times 10 to the 6 meters. And so G is equal to the gravitational constant, 6.67. And by the way, Cavendish did it about 100 years after Newton passed away. Per kilogram squared. Okay, and the mass of the Earth is equal to 5.98 times 10 to the 24 kilograms. All right, so we got all this down. Now, here's what I'm talking about. Let's top view. Here's the big old Earth. And here's a spy satellite. This is a spy satellite because this thing's moving fast. The closer it gets to Earth, because we know this. We know that mv squared over r is equal to g times me, m of the satellite, divided by r squared. Okay? Now, the smaller r gets, the smaller this r gets, the bigger the velocity gets. Let's take a look. First of all, here's the deal. And I know that R is equal to RE plus D. Okay, which isn't going to affect this RE too much. So that'd be 6.38 times 10 to the 6th plus 1.98 times 10 to the 5th. Let's go ahead and get that number taken care of. And then we'll do the quick and dirty algebra for it, and we'll be done with this. All right, so here we go. So we've got, add those two numbers. 6.38 second e to the 6th plus 1.98 second e to the 5th. Probably won't change it a whole lot. 6.57. Oh, I'm going to go ahead and just for my own, I'm going to go ahead and change this to scientific notation real quick. 6.578 times 10 to the 6th meters. Okay, that's my R. Now, let's just do the quick and dirty algebra here. mv squared over r is equal to g me ms, this is ms too, divided by r squared. So I've got r, but look what happens. I'll multiply r by both sides. Good. I'll divide ms by both sides. And I wind up with v squared is equal to gme over r. So as you can see, as r gets smaller, this v squared number is going to get bigger. So a geosynchronous satellite, which has a really high, which is way up in the air, which has a really high altitude, it's way up there, has a very small velocity compared to these spy satellites, which are very, very quick. So this just comes out to be the square root of gme over r. Okay, and I think the easiest way to do this is just to go ahead and take gme over r and then take the square root of it when we're done. So we got 6.67. So once again, let's put it up over here. 6.67 second e to the negative 11 times the mass of the Earth, 5.98 second e to the 24th, divided by 6.578 second e to the 6th. That's really fast, but I'm going to take the square root of that. .78 7 times 10 to the 3rd meters per second. Now, if I use our quick and dirty, 0.447, which gives me that meters per second to miles per hour, we can figure out how many miles per hour, because for us Americans, that's a speed that we can deal with a little bit better. Times 0.447, 3,480 miles per hour. All right. Those big jets only go, 600 miles per hour, 500. That's really fast. And since it's out of the atmosphere, we don't get a bunch of sound barriers. The sound barrier depends on the atmosphere and the temperature of the atmosphere and all that kind of stuff, the air pressure, all that kind of stuff. Well, that was fun. That was a nice little exercise, and I know this is the right answer. But let's just so you know that I know that you know, I'm going to go 7,787. Submit. Yeah, baby. Oh, they got 86. What's a meter? Off on that, meters per second. Okay, if you've made it this far, you're a trooper, and you're going to do great on the test, because we have covered what would be on chapter 6. And some of this planetary stuff, except for that stuff that I talked about in track 5, none of this is on your upcoming exam. It's just good stuff to know, and that's why it's on your homework.